In the vast universe, there are hundreds of billions of stars shining across the night sky. But just like humans, stars also have their own life cycles. They are born, live for millions to billions of years, and then die. When a star dies, it doesn't simply vanish. On the contrary, it can transform into some of the most mysterious and extreme remnants in the cosmos: white dwarfs and neutron stars. These two types of stellar remnants are the final products of stellar evolution, and although they are tiny in size, they possess terrifying density and power, challenging everything we know about physics. Before we dive into white dwarfs and neutron stars, we need to understand how a star dies. A star begins its life in a cloud of gas and dust in space called a nebula. Gravity pulls the material together, forming a new star where nuclear fusion in the core converts hydrogen into helium, releasing energy. This is what makes the star shine. But this fuel doesn't last forever. When the hydrogen runs out, the star becomes unstable. Its core contracts. Its outer layers expand, depending on the star's original mass. It will die in very different ways. Low and medium mass stars, right pointing arrow white dwarfs. Massive stars, right pointing arrow neutron stars or black holes. When a star like the Sun, or up to about 8 times the Sun's mass, reaches the end of its nuclear fusion phase, it is not massive enough to explode as a supernova. Instead, it sheds its outer layers into space, leaving behind an extremely hot, extremely dense core. This is a white dwarf. A white dwarf no longer sustains nuclear fusion, but it still glows due to the residual heat trapped inside. Over billions of years, it slowly cools down and fades. Size. Even though a white dwarf can have a mass similar to the Sun, it is only about as large as the Earth. That means its density is enormous. A single teaspoon of white dwarf material could weigh several tons. Composition. Mainly carbon and oxygen. Supported against further collapse by a huge quantum mechanical pressure from electrons, called electron degeneracy pressure. Future. After billions of years, a white dwarf would cool so much that it becomes a black dwarf a completely dark, dead object. However, the universe is still too young, so no black dwarfs are thought to exist yet. One very weird thing about white dwarfs: the more massive they are, the smaller they become. This is the opposite of what we usually expect and can only be explained using quantum mechanics. Less than break time equals ones. When a star more than about 8 times the mass of the Sun runs out of fuel, it ends its life in a supernova explosion. The blast blows off the outer layers, but the core is crushed so strongly that electrons and protons are forced to combine, forming neutrons. The result is a neutron star. Size. Only about 20 kilometers in diameter, roughly the size of a small city. Mass. About asterisk 1.4 to 2 times the mass of the Sun. That means asterisk 1 teaspoon of neutron star material would weigh around asterisk 4 billion tons. Asterisk rotation. Asterisk. Many neutron stars spin incredibly fast, sometimes asterisk hundreds of times per second. Neutron stars that emit beams of radiation as they spin are called asterisk pulsars asterisk the lighthouses of the cosmos. Neutron stars are the asterisk densest known objects in the universe, second only to black holes. Their gravity is so strong that asterisk they bend light, asterisk warp time and space around them. Their surface is extremely hard, like a solid slab of nuclear matter, and they can have magnetic fields asterisk millions of times stronger asterisk than Earth's. Feature: white dwarf, neutron star. Pipe dash 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 pipe dash 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 pipe dash 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 pipe. Mass: approximately 0.6 to 1.4 times the Sun, approximately 1.4 to 2 times the Sun. Size: about Earth-sized, approximately 12.000 kilometers, about city-sized, approximately 20 kilometers. Density: very high, extremely high. Composition: carbon-oxygen, almost pure neutrons. Does it shine? Yes. From leftover heat? No, except as a pulsar or hot young star. Nuclear fusion: no longer active, no longer active. Formed from medium stars, like the Sun, massive stars after supernova. Some neutron stars emit asterisk regular pulses asterisk of radio waves or gamma rays. These are called asterisk pulsars. Asterisk they spin very fast. Asterisk emit beams of radiation from their magnetic poles. Asterisk if these beams sweep across Earth, we detect them as rhythmic, blinks, or pulses, up to asterisk hundreds of times per second. Pulsars are so stable that they are considered among the asterisk most precise natural clocks asterisk in the universe, and have been used for extremely accurate timekeeping and tests of fundamental physics. White dwarfs and neutron stars may be the asterisk dead cores asterisk of stars, but they play vital roles in the cosmos. Asterisk recycling cosmic material asterisk. When stars evolve and die, they scatter heavy elements like carbon, oxygen, and iron into space. These elements are the raw materials for asterisk planets, life, and even humans. Asterisk creating gravitational waves asterisk. When two neutron stars collide, they produce asterisk gravitational waves asterisk ripples in spacetime. The first such event was detected in 2017, opening a new era of astronomy. Asterisk laboratories for extreme physics asterisk. They allow scientists to test Einstein's relativity, study ultra-dense matter, and probe the ultimate limits of physical laws. Good news, or bad, depending on how you see it. Our sun will not become a black hole or neutron star. It's simply not massive enough. Instead, in about 5 billion years, the Sun will expand into a red giant, swallowing Mercury, Venus, and possibly the Earth. Then it will shed its outer layers, leaving behind a hot core, a white dwarf. So one day, far in the future, the Sun will be just a small, dense stellar ember, slowly cooling in the dark. Every star's death leaves behind an important legacy. Some end gently as white dwarfs, glowing softly for billions of years. Some explode dramatically and leave behind neutron stars, spinning in the dark. Some are so massive that they collapse all the way into black holes, disappearing from the visible universe. They're like final chapters in a grand cosmic novel, where physics, time, and space all intertwine in strange and fascinating ways. White dwarfs and neutron stars are not just corpses of dead stars. They are living museums of the universe. They carry within them the history of stars, the building blocks of planets and life, and the clues to some of the deepest mysteries in physics. The next time you look up at the night sky, remember, the light you see from some stars may have come from suns that died long ago, and somewhere out there, their remnants, as white dwarfs or neutron stars, are still silently telling the story of the vast and mysterious cosmos.